Hi everyone. Last time we talked about turning points for polynomial graphs. That's where the derivative is 0. But what about where the function itself is 0? Remember that the real zeros of f of x correspond to what points on the graph? The real zeros of a function correspond to what points on the graph? Remember, f of x, think y. Where is y equal to 0? The real zeros of f of x correspond to the x-intercepts on the graph of y equals f of x. The real zeros of f of x correspond to the x-intercepts on the graph of y equals f of x. Y equals 0 at the x-intercepts. We wanted to find the real solutions for f of x equals 0. The x-intercepts correspond to the real solutions for f of x equals 0. The x-intercepts correspond to the real solutions of f of x equals 0. All right, so the real zeros over here, over here, over here, and over here. It looks like this polynomial function has 4 distinct or different real zeros. Let's talk more about these. Zeros and the factor theorem. Now let's say that f of x is a polynomial in x, and it's not the 0 polynomial. It turns out that 2 is a 0 of this function if and only if x minus 2 is a factor of f of x. And therefore, there would be an x-intercept at 2, 0. Likewise, 3 is a 0 of f if and only if what is a factor of f of x? X minus 3, in which case what will be an x-intercept? 3, 0. Now, negative 3 is a 0 of f if and only if what is a factor? X minus negative 3 or x plus 3. Negative 3 is a 0 of f if and only if x plus 3 is a factor of f of x, in which case we have an x-intercept at negative 3, 0. In general, if f of x is a non-zero polynomial and k is a real number, then k is a 0 of f if and only if x minus k is a factor of f of x. That's the generalization of what we talked about over here. And also, remember that with turning points, for an nth degree polynomial graph, we could have at most n minus 1 turning points. Actually, we could have as many as n real zeros, or n x-intercepts. An nth degree polynomial can have at most n real zeros, and therefore n x-intercepts. All right. So for example, let's find a third degree polynomial function that only has 4 and negative 1 as zeros. All right. Now, first off, because 4 is a 0 of this polynomial function, let's assume it's a polynomial in x. If 4 is a 0, then what has to be a factor? X minus 4 has to be a factor. If negative 1 is a 0, what has to be a factor? x minus negative 1 or x plus 1. Now, if we let f of x be this, will this satisfy the conditions here? Not quite, because what degree is this function here in purple? This would be second degree, and we're looking for third degree. So what can we do to up the degree? A lot of students would attach an x over here, but there's a problem with doing that. If you attach an x here, what else would be a 0? Then 0 would also be a 0, and that's not specified as a desired 0. So it's not appropriate to just attach an x. What would be another way to up the degree such that we're not throwing in any more distinct factors? We could square one of these. We could put the square over here, or we could put the square over there. Furthermore, we can multiply by a non-zero number. We could multiply by 2, by 3, by 4, by negative 100, whatever. In general, we can multiply by a, where a is a non-zero real constant. And again, the square can either go on this factor or that factor. And in fact, when you consider all these possibilities, this will represent all possibilities for third degree polynomial functions in x that only have 4 and negative 1 as zeros. These represent all the possibilities, where a represents any non-zero real number. So anything of this form or this form, a times the square of x minus 4 times the factor x plus 1, or a times the factor x minus 4 times the square of x plus 1. These forms only differ in which factor gets the square. Now, what are some differences, by the way? So over here in blue, what's going on with this blue polynomial? All right, well, you could say we have 3 real zeros for this third degree polynomial. Their names are 4, 4 again, and negative 1. I'm listing 4 twice because the exponent here is 2. And 2 here is called the multiplicity of 4 as a 0. So for this left form here, 4 is a 0 of multiplicity 2, corresponding to the exponent. That means that 4 comes in as a 0 twice. You can think of this as the factor x minus 4 times itself. And the negative 1 is a 0 of multiplicity 1. Negative 1 is a 0 of multiplicity 1 because the implied exponent here is just a 1. So there are 3 real zeros for this polynomial, but only 2 of them are distinct. There are only 2 distinct or different real zeros, the 4 and the negative 1. So if I just ask you to list out the real zeros, you can write them out with multiplicity. The 4 comes in twice. If I have something like x to the 10th, then 0 is a 0 10 times. 0 is a 0 of multiplicity 10. Look at that exponent. Likewise, what's happening over here in green? Tell me about this green polynomial for any non-zero value of a. What are the real zeros? Well, same as before. There are 3 real zeros, but their names are 4, negative 1, and negative 1. This time it's the negative 1 that's repeated. And this time, 4 is a 0 of multiplicity 1, and negative 1 is a 0 of multiplicity 2. All right, corresponding to the exponents here, 1 and 2. All right. Now, why do we care? Why do we care? Because of the following principle. If you have a zero, a real zero, of odd multiplicity like 1, that means that at the x-intercept, remember, real zeros correspond to x-intercepts. That means that you get a cut there. If you have a real zero of odd multiplicity like 1, then the x-intercept there has the graph cutting. The graph of y equals f of x cuts at that corresponding x-intercept. And I'll show you what I mean by a cut. Okay. Likewise, if you have a real zero of even multiplicity, like 2 or 4 or 6, then the graph of y equals f of x bounces at that x-intercept. Basically, if you have odd multiplicity, the graph acts like a snake around that x-intercept. If the multiplicity is even, the graph acts like a bull, and you bounce. So it's kind of like snake versus bull. All right. So let's take a look at these graphs. And if you want, you could expand them out. What do these graphs look like? All right. If I take the first case, the blue case, where a equals 1. If a is 2 or 3, that's just a stretching. Let's take a look. Now, as we look left to right, if we expand this out, the leading term is going to be x cubed. You could judge that from here as well. But you can tell even from here that the leading term is going to end up being x cubed, which means that overall, we're going to end up with what kind of shape? It's going to be a rising snake, which is going to go up, up this way, down, down this way. It's a rising snake. So what's going to happen? We go up to, all right, well, here's -1. At -1, we have an x-intercept. -1 is a zero of multiplicity 1. Because the multiplicity is odd, what do? Do we cut or bounce? We cut because 1 is odd. We cut. The exponent is even on the factor. We cut. Now, I don't know where this graph peaks, but I do know it's got to fall down to earth because we have another 0 at x equals 4. So I don't know where it peaks, but it's got to come back, and we get another x-intercept at x equals 4. The multiplicity there is even. The multiplicity there is 2. 4 is a real zero of multiplicity 2. Now, because the 0 is even, that means that the graph is going to bounce off the x-axis. The graph's going to bounce off of the x-axis. All right, so the graph bounces. All right. It's a rising snake. It goes on, on. And this is a basic sketch of the graph. X-axis here. Y-axis, but I don't know if the peak is going to be in quadrant 1 or quadrant 2. Let's see what Desmo says. Y equals the square of x minus 4 all times the factor x plus 1. So what's happening? The graph comes up from hell at 4, 0, and at -1, 0, there are x-intercepts. The graph comes up from hell at -1, 0. Exponent is 1. The graph cuts through the x-axis. It turns out the graph peaks here. We have a local max point in quadrant 1, but I didn't know if it was quadrant 1 or quadrant 2. On homework, I wouldn't expect you to know that. It turns out to be quadrant 1. That's where the derivative is 0. The graph comes down. We have another x-intercept at 4, 0. The exponent there is even, though, at x minus 4. Bounces. The graph goes up, up, up. Overall, we have a rising snake. Also, what else do we know? Well, if you plug in x equals 0, or if you expand it all out, you'll see that the constant term is 16. That tells us what? That tells us that 0, 16 is the y-intercept. So we know a lot about this graph. We know about the intercepts and the overall long-run behavior. That might be all we need to know. Now, question. Again, here's another version of this sketch graph. What if we put the square on the other factor? All right, so let's take a look at f of x equals x minus 4 to the first, and then x plus 1 with that squared. What is this going to look like? All right. If you expand it out, we get x cubed and then lower order terms. All right, overall it's going to be a rising snake again. Up, up this way, down, down that way. Again, we have x-intercepts at -1 and at 4. Now this time, as we go up to the x-intercept at -1, 0, since the exponent is even, the multiplicity is even, that means we do what? Do we cut or bounce? Since the multiplicity is even, we're going to bounce. We're going to bounce. So we bounce. If you plug in x equals 0, we end up with -4. So 0, -4 is going to be our y-intercept over here. The graph's going to turn around. I don't know if the graph turns around in quadrant 3, but let's assume it's quadrant 4. All right, comes back up, and then x equals 4, it happens. Well, since the graph's going to go up, 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 I think it's going to cut, and it's going to cut. 1 is odd multiplicity. That means we cut through like a snake. We bounce like a bull over here at -1. Here at x equals 4, we cut like a snake, and then up, up, up. And lo and behold, let's graph that. Y equals, it was x minus 4 times x plus 1, and that's squared. Yes, we have a rising snake overall. We go up to the point -1, 0. We bounce. We have the y-intercept at 0, -4. It turns out that the midpoint is in quadrant 4, not quadrant 3, but in calculus you'll find that out. Then we go up, up, up. After the midpoint, we go up, up, up. And then at 4, 0, we cut. And then we go off, 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 like a rising snake. All right, so we know a lot about these graphs. And by the way, you're allowed to put a non-zero constant in front. What if we multiply by 2? Stretches the graph. By 3, by 4, and so forth, stretches. 0.5, that's a squeeze. 0.4, 0.3, 0.2, 0.1, that's a vertical squeeze. But still, the x-intercepts stay the same. The x-intercepts stay the same. And we still have the same bouncing and cutting behavior and the snake behavior. What about a negative number? What happens? If I multiply by -1, what happens? Upside down. But same x-intercepts. And we still bounce here, we still cut there. But this time, it's a falling snake. And the y-intercept also gets flip-flopped to 0, +4. All right. And then -2, -3, we stretch. But I put an a out here. All right. I have the same x-intercepts, same bouncing and cutting behavior. Rising snake here, falling snake here. If I put the square over here, we get those other guys. And that corresponds to all. So let's do that. I'll put the square over here, cut this out. All right. All right. So we get all these guys. And together, these form all the possibilities that will satisfy these specifications. Third-degree polynomial function in x with only 4 and -1 is zeros. We looked at all the possibilities. Wow. All right. And again, the even and odd multiplicities, they correspond to bulls and snakes, basically, locally around the x-intercepts. So the graph is kind of like a snake near -1, 0 here, and kind of like a bull, and kind of like a bull at 4, 0 over here. All right. Next, a few final comments.